this is one of the first places where you begin to have that confusion, right? We talked about how
a little bit about
I-class
casinos
SE
for the
gets
people
reused
like
over
me
and over.
who might not
So
have
now
known
we're
about
talking
casinos.
about I-class SE
They obviously like a lot of
cards
money. They have a
specifically.
controversial history.
So
And there's a lot of
just took the
reasons why that history is sort of controversial. Casinos are a hotspot for money laundering because it's an easy way to move funds around. Particularly in Australia, there's been some controversy lately. Our two big casino brands, Star and Crown, had to pay big fines because they didn't comply with anti-money laundering laws, and there's been royal commissions and stuff. It's the same in other countries as well. Casinos are getting a little bit of heat, so security is important. They use AI, obviously, otherwise this talk wouldn't have gone as I planned. And they use AI for lots of different reasons, and as we'll go into later, they rely specifically on facial recognition and person detection. But the landscape is really interesting when it comes to casinos because just like any organisation, they're trying to figure out exactly what the most strategic or the best way of actually adopting and integrating AI is. And just like any organisation, they have to rely on third-party providers for the most part. Or they can bring in their own consultants, but that's sort of expensive, and not all casinos can necessarily do that. And there are also a few companies that provide AI services to casinos that are already providing things like chips and cards to casinos as well. So it's a very small space. When I first started this talk, I thought that things like card counting would be a use of AI in casinos, and it's not. So you're probably familiar with card counting, and it's not illegal, it's considered advantage play. So a casino, however, does have the discretion to prevent people from playing there for any reason. So if a person is very ostentatiously card counting and winning a lot of money, probably the casino is going to not want to have them there. But it was interesting because I expected that things like card counting would be a big use case for AI, and it wasn't. So how do we actually hack an AI? This is the first bad joke of the day. So when I first told my mum I worked in AI, she said, "Oh, darling, what are you doing working in artificial insemination?" Because, I know that was a pity laugh, but thank you. She works in medicine, and so to her, that's what AI is. And so obviously for most people here, AI is artificial intelligence, but even though we know it means those two words, what people have in their mind when they think of what artificial intelligence is definitely differs. Some people imagine Skynet and things like artificial general intelligence. Some people imagine algorithms, machine learning systems. Some people just imagine anything that's sort of at the cutting edge of technology. So when we think about how to hack an AI system, we really have to think about the actual technology that we're trying to hack rather than some sort of AGI-related goal. So I'm focusing very much on machine learning models. But if we really think about the history of AI, and if we think about it as just something that does something a human might otherwise have done, the idea of hacking AI has been around for a long time. So this is an example from a casino context. So as we know that there are no random numbers in computers, right? It has to be an algorithm. And so there are some pretty high-profile cases of people being able to basically hack the algorithm. People who have access to sort of the seed information of these algorithms have been able to steal money, pretty large sums. In 1995, Ron Harris was able to steal $100,000 this way because he knew about the algorithm and was able to predict the next numbers very successfully in a game of Keno. I hope they're not having more fun than us because they're very loud. Do I need more bad jokes? I don't think you really want that either. So that's one example of hacking an AI, I guess. And the other is sort of card counting. So if we think about it, the reason that the casino always wins, right, is because the game is statistically in their favor. And that goes anywhere from sort of a 2% to a 25% advantage, where 25% would sort of be the slot machines, and then 2% would be a game of blackjack. And that's why card counting in blackjack is most likely to be able to reduce the casino's favor, because if you use perfect strategy, which is just doing the plays that are statistically most likely to have you win, plus card counting, you can reduce that to closer to zero. And the only reason that the slot machines are 25% max is because of regulation anyway, otherwise the casinos would probably want them to be higher. But that's an example of algorithm hacking too, because you're hacking the statistical process of being able to do that. So when we think about the modern iteration of hacking an AI system, we come to the realm of adversarial machine learning. And everyone probably has seen this picture before, so I feel like I have to show it. But basically the idea is that you're able to create specifically crafted adversarial examples that you can then input into a machine learning model to make it not do what it's meant to, basically. So this example is from 10 years ago, and this is like an image of a panda where you can have an adversarial example superimposed on top of that, which is just perturbations to the image specifically crafted based on the target model that you're trying to attack. And it can disrupt or deceive the model really successfully, even though a human can't recognize it. So adversarial machine learning is the field that my PhD was in, and you can consider it sort of the offensive side of AI security. It's basically the field that is coming up with the attacks. But it's traditionally been very academic. Recently, we're starting to see more examples of these kinds of things in real life. So being able to actually implement some change in the physical world that's able to prevent, say, autonomous vehicles from being able to recognize stop signs, so they drive straight through. And in terms of the landscape of adversarial machine learning attacks, it's massive. It's just exploded over the last 10 years. And if we think about all of the different attack surfaces represented by AI systems, so on the top, things like convolutional neural networks, which is a machine learning model really good at computer vision, versus something like a transformer along the bottom, which is very good at natural language processing and the backbone of things like GPT. They're very different attack surfaces, but many different adversarial machine learning methods now exist that are able to very successfully do bad things at each stage of that attack surface. So most of the time, these attacks require you to actually change something about the object itself, right? So you have the panda example before. We have things like adversarial glasses that prevent a person being recognized from detection. You have like a jumper that can also hide a person from person detection. And the example I love on the bottom right is this DARPA model that was meant to be used in sort of urban warfare environments to detect people. And they asked their Marines to try and red team that model. And they found that the Marines could just act not like people and very successfully deceive the model. So they did things like put cardboard boxes on their heads, they waved branches around and acted like trees, whatever that means. And they were very successfully able to hack the model. The challenge with all of these things is that you're actually required to change something about the object itself that's being classified. There are some examples of attacks where you don't need to change the thing itself. This is called an adversarial sticker. So if I put this next to something else, a model is going to predict that this is a toaster. So if I put this next to a banana, which is the sort of the example that they give, instead of recognizing the banana, the model is going to see a toaster instead. However, this is sort of challenging because this is very obvious. If I put this next to a banana, I'd be like, that's not meant to be there. That's a banana. But a model doesn't see it that way. So I had a thought. I was like, what if you could change something about what's in the image frame itself, but you didn't have to perturb the actual image? And so I came up with this technique called distributed adversarial regions. And this is part of my PhD where I was sort of coming up with this attack. And so the intent for this was largely in urban camouflage environments. So being able to do things like have specially crafted buoys around ships, for example, like military ships. So you think it's a container ship. Things like have specially crafted buoys around ships, for example, like military ships, so you think it's a container ship instead, or having it around other different kinds of military platforms. And if I can easily get the video working, this is just a very quick example of what this would look like. So if you have these sorts of buoys around, that's a Japanese U-boat, you can actually prevent the model from recognizing that platform. Also, don't come at me for them not being real buoys. It would have been a very expensive endeavor to put buoys around a vessel. The thing about being able to digitally manipulate the images is that it's a really good surrogate for not being able to actually change the physical environment and being able to test it. So I wanted to see if I could apply this technique to things like facial recognition for this casino context. So how does this relate to casinos? I assume everyone here is familiar with the Ocean's 11 franchise. Yes, I mean, it's a heist, you know, like we don't need to get too thicky about it. The idea is that we're basically just bypassing all of these different security levels that they have in a really cool way. Ideally, there's like bourbon and suits and George Clooney. I did not get to have a George Clooney in my life doing this talk, but that's okay. So we get the premise of the heist. This is what I wanted to do. I wanted to understand Casino Canberra's, I don't know, AI operational environment. Then I'm going to pick some target models to create this attack. I'm then going to, you know, implement the DARs, the distributed adversarial regions. I'm going to test how I can sort of disguise them in different ways, and then lessons learned and sort of next steps. So the first step. I mentioned my PhD. I've been doing it part-time for a really long time, so I feel like I should be finished, but I'm not. Now this is annoying because it's really hard to like simultaneously try and build a startup and also finish a PhD. My supervisors, only one of them knows I'm here right now. The others think I'm in Canberra, like working from the university. So don't tell them. But the good thing about still doing a PhD is not only do I get really good student discounts, but people are very helpful. So if I reach out to people and I tell them that I want to do something as part of my PhD, people generally say yes. It helps that I'm also sort of like nice and polite, and you know, people are always just very helpful. So this is what I did with Casino Canberra, and they were very willing to help, which was nice of them. So this is Casino Canberra. Maybe it doesn't look like the Bellagio or the MGM Grand, but like they have a red carpet. It's very nice. It's right next to our civic centre. It's between there and the convention centre. It's, you know, they do okay. They're very excited about a new upgrade that they're doing. They're going to get a lot bigger. There'll be a hotel. They've got it going on. So as part of this upgrade, they're thinking about implementing artificial intelligence for the first time. Something I was really interested to learn through doing this sort of research was that facial recognition and person detection was by far the largest, like the most important form of AI for casinos, but it's obviously very unequal in how casinos are able to. Detection was by far the largest, like the most important form of AI for casinos, but it's obviously very unequal in how casinos are able to. In fact, they would actually build their casinos using this AI in mind. So when we walk around the casino, you might notice that sometimes there are like sort of narrow corridors that you're forced to walk through, and that's to make sure that your faces are actually caught by these cameras. So as a casino like Casino Canberra is thinking about their redesign, this is very much inherent in how they actually decide to design the casino, so that they can use things like facial recognition to identify money launderers or known criminals or card counters, I guess. Also problem gamblers. There are some nice use cases for it as well. They want to make sure that people aren't gambling too much, just the right amount. And things like number plate recognition for cars is also really important. But in terms of AI, this is very much a computer vision problem. So being able to see things in the environment and understand it. They don't really have a lot of use for other kinds of AI right now anyway, not things like chatbots or signal processing. That's not really in their realm. But right now, they're also very much dependent on people, just being able to identify those known people and then log them in the system. That's very much still dependent on humans, even here. So what I did next was I need to choose the victim, right? Like I said, Casino Canberra doesn't currently use AI, so I couldn't really use any live facial recognition that they were using right now. So instead, I had to pick an appropriate victim that would be close enough to something they would use. And you might. However, it's not, fortunately, because of this principle in machine learning and its convergence. I don't know if this works with a big crowd, but I might try some audience participation. I don't know. Does anyone want to shout out and guess what this number might represent? I actually can't hear anyone anyway, so I'm going to assume that maybe one of you was right. So this number actually represents some significant research into similarity of models. So if you have a model trained on similar data to do similar things, you end up with a similar model, like basically the same model. And this is actually really significant. A lot of the models that companies rely on and produce as part of their IP are very much, or exactly the same as open source models. And in fact, a lot of the time they do actually just use open source models and then do a bit of fine tuning. And that doesn't necessarily change the model itself. It certainly doesn't change the architecture. It might change, sort of how you apply it to different use cases. But a lot of research has been done to show that if you compare two models, an open source model with a model that is a company's IP to do things like facial recognition, they are 95 to 99% similar. It's a minimum of 95% similarity, which is really significant because it means that I don't really need to, do anything too difficult to be able to find a good victim model. So that's convergence. So there's a lot of different victim models that I wanted to test. Like I mentioned, I already did this attack for things like urban camouflage, so being able to do things like object detection and testing some of those models. I also added some of these facial recognition models as well. These are just a few of the open source models available at the moment. So the next step is to create these distributed adversarial regions. And this is a fairly boring diagram, so maybe I'll show you instead a slightly less boring video. It's very hard trying to create fun demos for this, I don't know. So maybe I need to find a way. So this is the video that I'm testing on, right? This is me walking up to the detection. And this is me implementing the attack on one of my target models. So I'll talk through the method because it takes a couple of minutes. But basically all I need to do to implement this attack is to perform an optimization algorithm on the video in question to identify different regions where if I perturb them in certain ways, they're going to cause a misclassification, which sounds really easy. But the difficult thing is in sort of making those areas not too obvious, or at least being able to pick a few different regions that could reasonably actually be altered. And so this code shows me being able to perform that optimization based on one of these victim models, making a prediction on this video. If you're not a person who finds the code interesting, maybe at least the thing you can take away is that it only takes a minute to do. It's very easy. And I don't even need to use an existing pre-built library or anything. It's just an optimization algorithm. So when I said before that there's over 100 different kinds of adversarial machine learning attacks, it's really easy to just sort of build them yourself. It's all optimization at the end of the day. So we can see on the screen here that the code wrote out no match found, and then when I add the perturbed image, so there was a match found for the clean image, and then when I added the distributed adversarial regions, there was no match found. So the interesting thing about being able to do the testing, or maybe not the most interesting thing actually, but the process of actually thinking about the attack surface and, let me skip through here. Thinking about the actual attack surface and what we're affecting in this attack. So most computer vision relies on convolutional neural networks because they're the most powerful sort of model to be able to do this. And being able to create attacks that work for most of them is actually pretty easy. So if we think about facial recognition, the way that it works is that it sort of takes your facial geometry and then is able to compress it into an embedding space. And being able to identify clusters and sort of relationships between them, and then based on that mapping, be able to identify me versus not me, I guess. And so when I have that information, I can do things like create specific patterns that change that distribution. So if I go back and play this other recording, I want to be able to test doing things like creating jewelry. So this is the example that I'm testing. So the challenging thing about building models or thinking about model security is that all of these models that I'm testing on, it doesn't actually take much to be able to disrupt them. Creating this attack is really very simple. Just sit here a minute. Let me skip back to the slides while this loads. So maybe it doesn't look so interesting, but being able to do that attack and like have it not recognize me, I guess that's a way of saying that I hacked the model, right? I mean, it was able to not recognize me because I created these sort of adversarial earrings that, you know, when the model looks at that image of me, it doesn't recognize me. When I test it, that's the important part of the process, right, from a machine learning perspective. This looks very boring too. I tested all of those different models and I wanted to see the extent to which the attack actually works and decreases the confidence level of that attack. As a way of distilling all of the sort of the boring columns in the graph, the number that we ended up with was a 40.4% reduction in like confidence. So what does that actually mean? Is that significant? When I implemented this attack on the urban camouflage environments, it was more successful, honestly. It's a bit easier for things like ships and military platforms because those models tend to rely a lot more on context. And in facial recognition, it's a little bit harder because a lot of models would tend to look at the geometry slightly differently. But 40.4% on the whole of all of the models that I tested is actually really significant because that means that if I have, say, a confidence threshold of like 90%, so a model looks at an image of me and says with 99% confidence that it is me, being able to decrease that confidence by around 40% means that if it was originally 99%, then it's going to be 40% less than that and it's not going to meet that threshold. So I don't actually need to affect a massive change in the model to be able to have it not recognize who I am. And I guess a way of thinking about that is by calling it context. But really what it means is that most of the models that are already out there, all of the open source models that we use and data scientists use and organizations in fact use and then fine tune are vulnerable to an attack like this, which is really very simple, you know? What I did by adding, you know, regions of perturbation to myself is definitely not the most sophisticated kind of attack. Yesterday I was at an AI security forum and it was amazing because everyone was sort of talking about all of the latest breakthroughs in AI security and how we can make models extremely secure and the technical and the governance things. The really challenging thing though is that most organizations don't have that existing level of maturity. And the kinds of models that they're using are these kinds of open source models that only take a few regions to be disrupted and to cause a misclassification. And thinking about thinking about what this actually means is really significant because while I've applied this to a computer vision use case, so this could work for things like retina scanning, number plate recognition as well, without actually having to change the object itself, but just changing things around the object, really just highlights how brittle most models are. It also highlights that while I did this in a computer vision use case, because that's sort of what works for this facial recognition casino context, exactly the same kind of attack could be applied to different domains as well. So things like natural language processing and signal processing. Use case context, natural language processing does all the cybersecurity applications as well. So being able to identify malware, being able to
identify
like good versus bad code, they're natural language processing problems. And if we can add perturbances that are actually not about the thing that we're trying to classify, but are still able to disrupt the model, that's a real problem. It's the same in the signal processing space. That's things like RF and audio and LiDAR, you know, all the signal processing problems we have, medical imaging, being able to add perturbances that aren't even related to the thing that you're trying to classify represent a massive problem. I did some other research that information and have it alter the messages that they were giving. And we found that after sort of a few simulations and a few iterations of being able to add this additional kind of like noise material, they did actually successfully adopt these other ideas, even if that wasn't sort of encoded into them already. When we think about attacking machine learning models, the challenging thing as well is that it's not the same as cybersecurity. Like when we think about testing model and identifying what makes a good model, data scientists will use scores like this. So they look at accuracy, they look at precision, recall and F1 score are sort of related to precision as well. They look at all the statistical functions for a model that makes it like largely accurate. But the security is rarely ever considered, and it's a very different problem to a cybersecurity problem. I mean, what does it mean to hack an AI system itself? You know, I sort of looked at that 40.4% number and felt a little bit disappointed. Like, I sort of wished that it was a bit more definitive. But the thing with hacking an AI system is that it's not really a binary, did it work or did it not? But it's more about, on the whole, we were able to reduce the classification confidence of a model. So it's better to think about it as part of the kill chain. And quite a lot of the attacks at the moment are very much sort of like a Stuxnet equivalent. You know, they're very complicated, they're very difficult to implement. That's why there's this idea that they're a bit more academic than realistic or practitioner-based. Whereas even though being able to add like these random distributed regions to an image isn't all that sophisticated, the fact that it works and it actually disrupts a model most of the time is a real problem. And it's sort of more akin to like the DDoS attack equivalent in a machine learning sense. Because even though that number was 40.4%, in our experience, if you're able to leverage some sort of AI attack or some sort of adversarial machine learning attack, you're able to hack the system 100% of the time, because there's always a way that you can adapt it for whichever case study you need to. So the fact that so many organizations are reliant on these like inherently insecure models is a real problem. Because AI security is real. So if we're thinking about like next steps and lessons learned from an attack like this, we already have a few companies starting to put out reports about the incidence of AI security related attacks. And it's changing a lot. Like it's encouraging that since I started in the field, it's definitely being taken more seriously and we're starting to see these incidents. But it's really unfortunate because we have so many lessons from the field of cybersecurity that we could bring into the field of AI security, but they just aren't. So it's really important that all of the cyber folk in the room are thinking about how to solve these sorts of problems in AI security as well. Some of the, as I mentioned, the interview with Casino Canberra was part of many other interviews we've done, and we've got these interesting insights already. 94% of the people in organisations we spoke to could articulate how they use AI, even if maybe it's not what everyone would define as AI. They had an idea of how they use AI, but only 8% could articulate how they secure their AI, and most of the time it's never really considered at all. The other reason I wanted to use the casino case study was because a casino is a really good sort of analogy for a society that it's starting to be built around surveillance as well. like casinos are built with surveillance in mind, and societies are increasingly sort of moving towards using more AI, specifically facial recognition AI, to do important things as well. So the important thing to think about from like the perspective of actually what you can do with the knowledge of these attacks is that even now in the casino environment, it's still entirely reliant on people and process. And especially as organisations like casinos are going through this inflection point in adopting different AI technologies, being able to actually like govern that and implement it well is still really hard. And even though over here we have lots of very technical and mature conversations about it, most organisations out there are still really grappling with how to do it. It's still so reliant on having people to surveil it. And at the end of the day, I went into Casino Canberra. I asked very nicely if I could try hacking their things, and they said yes. So what does it really mean? In terms of what Casino Canberra is able to do with this, it's tough because they're reliant on third-party AI. So all you can do is sort of ask the questions and hope that you keep it in mind. But we're really so reliant on these organisations that provide the AI, and there's no regulation around how they have to actually secure them or make sure that they're robust. So it's really challenging, but at least being able to ask the question, it sort of helps. So that's it. I am talking tomorrow as well about my experience in the Australian government. I worked at an intelligence agency, so I'm also speaking in the policy village on one of the creator stages about sort of the policy element of these AI security attacks as well. So thank you so much for coming, and please do keep in touch.
We could now provide that role to the service and arbitrarily assume it and access whatever resources. This is an example of a cross-service confused deputy attack, where a lower privileged entity, in this case us,